Good afternoon. In case you can't tell, I'm Peter Weismantle, and this is Luke Leung.
That would be me.
Luke Leung, unfortunately, has left SOM, I have to correct Steve, and is now with the Director of Engineering at A. Epstein, in the interest of full disclosure.
Correction.
But we spent about 4 years joined at the hip doing the Burj Dubai, Luke the building services, and myself doing the architectural technical. We're going to talk about sky source sustainability, and I'll be very frank. This again, a lot like Roy's discussion. It may raise some questions. It may hopefully it will generate some interest and some conversation, because a lot of the things that we kind of discovered, and everybody that's a designer here knows that when you start a project, no matter how big or how small it is, you always discover things. And on a big project like Burj Dubai, we were discovering things all the time. Because we really are kind of in uncharted territory, let alone understanding wind and other things. But we thought to ourselves, what are the advantages of building tall? We think about sustainability, the earth, and other things. We think about photovoltaics, we think about wind, but what other elements that are inherent in a tall building could we take advantage of? Things like the delta T, difference in temperature, difference in air density, the difference in solar radiation, moisture content, and of course wind. Why don't we hear about those other elements? Because they do vary with height, sometimes linearly, sometimes as a more geometric function.
Well, just touch on this quickly for Peter. Linear element at the middle of the building is a good indication of how the whole building performs. Think about it, linear, right? So if the building is 500 meters, this is the temperature drop of a tall building. At the midpoint here is 43.7 degrees Celsius, given this is Dubai, designed at 46.1 at grade. But if this building goes up to 1 kilometer, then the average temperature will become 41.2 degrees Celsius. So now all of a sudden you have, in this case, 3.8% drop in temperature, in this case, 7.0% temperature drop at the middle of the building, which is a good indication of the linear elements, which is temperature, density, and maybe moisture. But it's not a very good indication of the wind and stack effect, maybe.
For the examples that we used in our paper, we assumed a 1 kilometer tall tower in Dubai, and with a floor plan similar to the mid tower of Burj Dubai. That is to say, probably about 20,000 square feet.
And the focus of our discussion is on cooling loads, how the envelope performs, and the ventilation air, not necessarily with elevatoring and HVAC system. That adds complication to the discussion. Let's look at first thing, temperature. Most of you know that temperature drop with elevation. If you use the H-rate method, if the ground is at 46.1 degrees Celsius, the top is at 39.6. If you assume the air is relatively dry, then if the ground is 46.1, at the top is about 36.3, a 44% deduction for 1 kilometer tower right here in Dubai. Those are the chart of the two temperatures. And one way you can take advantage of that is take advantage, because in Dubai is mainly cooling predominant climate, so you can take advantage of the lower temperature air at the top of the building. The reason, because the two temperature drop difference is in moisture content in the air. Many of you wake up this morning will find the outside is kind of moist. Whenever there are moisture in the air, high moisture, as temperature drop, moisture tend to condensate. When it's condensate, it releases heat, and that's why that offset that dropping temperature effect. Now, for those who are involved in construction, you may want to take that as a VE item, right? Size the cooling plan on the taller part of the building with a lower design temperature. You have to be careful because there are temperature inversion, like what we experienced this morning. The ground is actually condensed and forming clouds. What's the benefit of that? Lower temperature in cooling predominant climate like here, it will reduce the conduction heat gain. Infiltration is at a lower temperature. And also, maybe most important, increase the radiant comfort. Don't forget, S-ray, the latest round of comfort, actually tells us 50% of our comfort is coming from radiant temperature. Only 50% is the thermal temperature of the air. If you do that, the load saving is 10% compared to the same environment all through the 1 kilometer tower. The next thing we'll get into is moisture. This is a distribution of moisture with satellite data around the world. And this is what happened with the moisture. Notice right here at 1 kilometer, moisture most likely will stay maybe even or even less as you move up, as you can see here. The red and blue line is two different sets of satellite data. Again, the moisture drop, because its temperature drop, it tends to condensate out of the atmosphere. In this case, the outside end temperature is about the standard atmospheric temperature, so it's about 20 or so degrees Celsius. As the moisture warms up in the summer, you may not be able to drop as much moisture in the air because now the hotter air can accommodate more moisture. Why is it important? Because for those who live in hot and humid countries like Dubai, like Hong Kong, southern coastal China, etc., you will know that moisture is a big thing to deal with. Dropping moisture actually reduces the ventilation latent load, reduce the infiltration load, especially at the top part of the building, and also reduce the moisture-related issue. The total drop in the cooling load, it could be up to 0 to 4% depending on the amount of moisture.
Solar radiation is an issue, and it, again, as you would guess, it varies, but it doesn't necessarily vary as you think. There's in the air, especially if you've been around Dubai more than a day or two, you'll see that there's another component beside oxygen and nitrogen. It's the aerosols. It's the particulate matter in the air made up of windblown dust. In the case of a marine climate, salt from sea spray, et cetera, sulfur dioxide and soot and smoke, and of course, dust, sand. Aerosols will impact the amount of available radiation. And this is a really pretty true view of Dubai on a pretty typical day.
Sorry.
Yep. Well, the radiation on any particular structure, there you go. It's working. Radiation on any particular structure is made up of several components. Obviously, direct irradiance right from the sun, reflected or diffuse irradiance from the sky, and then diffuse from the ground. So those three components. All these elements can't necessarily be taken for granted. So field measurement is always important. Solar radiation, this is a kind of an interesting graph in that if these are baseline elevations, so the bottom curve is the irradiance at 1,000 meters. The top curve is the irradiance with a ground level at sea level. So it's a little counterintuitive. You expect that the higher you are, the more irradiance you would be able to harvest. But it's counterintuitive because of orographic uplift. And basically, the bottom line is, I hope that wasn't me, as the warm, moist air rises, as it passes over a mountain, for instance, it becomes, in essence, more saturated, producing clouds, therefore reducing the amount of sunlight available.
And on the other side of the mountain, similar thing happened because as temperature dropped, there's actually more possibility of cloud formation at the top of the mountain. That's why at the top of the mountain, usually worldwide in most cities, you get less sun than at sea level.
So what does that mean from an architectural standpoint? You might consider orientation and extent of glazing to augment or mitigate solar impact, to equalize it or to augment it.
Air density. Air density drop with elevation, as most of you may know, because the pressure drop with elevation. And that's why your ear pop when you get up to a high-rise building. This is interesting for those who are mechanical engineer, but even if you're an architect. Notice, don't worry about the unit here. That amount of ventilation air at the top of a 1 kilometer tower, it is 100%. At the bottom of the tower, because now the air is less than as at the top, so there's actually less mass. At the bottom of the tower, you got only 88% of that number. And if you move that number to standard atmosphere, you got about 19% saving. So the question you ask yourself is, am I at the top of the tower, I get less air, I got less oxygen, is it bad for me? As far as we can see, all the research indicate the amount of oxygen difference is too little for us to notice. But the benefit of that is, now you have less cooling energy you have to deal with because the air is less dense. And then also because less dense air requires less energy to move it. So that's actually another benefit for the tall building, especially at the top. And the total cooling load saving in the hottest hour, again, is the lowest. It's about 3 to 4%, simply because the air is less dense to deal with.
From an architectural standpoint, it means that we try to locate fan rooms higher up in the building and take advantage of that by pushing the cooler air downwards. Wind is something that everybody's going to talk about today, and so we'll talk about it also. And obviously, we talked wind speed increases with elevation. Wind speed varies with location on building. This is a diagram of Burj Dubai, the wind pressures. You can see around the top and at the corners and edges, we start to get concentrations of pressure. So obviously, why not shape the building to concentrate the wind? And we've done projects like that where we've gone to quite extensive means to shape the building. To then take advantage of the fact of, put a turbine in that little pocket and you generate electricity. The question is it how efficient is it? And, I think we have a little common theme here. From the standpoint of just fundamentals, just simplicity, you can only get a certain amount of efficiency out of the turbine. And especially if you're trying to do things with it, why not really try to utilize it directly?
Yeah, I mean, Peter's point is, if you use a vertical turbine, the maximum theoretical efficiency you can get is 59.6% of the wind power. That's it. And since most of the wind power is not even getting there, so you may get 30 to 40% of the wind energy actually go into a turbine. But if you use the wind as direct natural ventilation and just use the wind to blow right into an air handling unit, you can possibly close to up to 100% of the wind energy directly into your fan or into your space.
So how did we take advantage of it before we invented all these fancy high technology systems and high energy uses? Obviously, the traditional wind tower is a form that you'll see here in the Middle East, especially in Dubai. It's almost the national symbol. How can you apply that on a larger project? And so there's a project that we've done in Zhengzhou, China. It's a hotel with a large atrium, 86-meter tall atrium. And one of the challenges we had was that there are certain times of the season where you can take advantage of that natural ventilation, where the air is not too moist and it's kind of the right temperature. So how can we as architects help that without going to all the extent of the high-tech solutions? And so we did a finite element analysis study. The concept was you have an inlet low in the building, in the atrium, and then you have an outlet at the top, and you try to locate those in as propitious a location as you possibly can. So some of the case studies that we did looked at wind speed of 4.5 meters per second, and outlet and inlet sizes of relatively small when you compare it to the volume of the atrium. And those analyses showed that if you had a case 1 in this direction and a case 2 in this direction, the bottom line was case 1 gave you about 5 times the amount of ventilation.
Right, simply turning the opening, if you're facing the wind, you will get 5 times as you turn the opening 45 degrees, just subtle differences like that.
So you either work with the prevailing wind, or you actually build in a system that allows you to actively or dynamically change the location of that opening.
In a cooling predominant environment, you can decrease the cooling load by about 1% using, the fan and the wind to help you, and it can decrease the motor horsepower of the fan. Combining all the above, we have temperature at about 10%. Moisture, we did not take any benefit because in Dubai, the summertime is about 46 degrees and 30% relative humidity. It's just so hot that it doesn't able to get much moisture out of the air. But in the part low Dubai, then you can during transition season. Air density, we get about 4%. Wind, because the high wind actually increase the conduction heat gain, right? Because as the wind temperature pick up, you actually increase the conduction heat gain, so we have to minus 1%. So for 1 kilometer tower, just on the loads alone, forget about elevator ring and the other elements for a second, that could be a 13% reduction potential. Something we also talk, something actually will be beneficial is how about your mean radiant temperature comfort. Now you have a cooler building on top of the 1 kilometer tower. It's less harsh environment, and then possibly you can utilize the wind to take 100% of the advantage as a, as an intake to your fan system. There's another study out there done by the National Renewable Energy Laboratory on Freedom Tower, and they have similar result, but since it's that is in New York, so the climate is a little different. What they find out is due to temperature saving, you have about 2.6%, but the biggest saving is in shading in an urban environment, up to 9%. That's why the latest generation S-Ray coming out with a standard and the LEED standard, all those are kind of pushing this very high efficient, low carbon building towards an urban environment. And in their case, they have actually about 12.8% saving in the loads. But what didn't talk about in the paper is air density, humidity, and stack effect, and etc. were not quite addressed.
Now, why is this all important? I think who would have thought it, 6 or 7 years ago? We're living in an age of new super tall buildings, and the magnitude of these new buildings is something unprecedented. If you look historically back at the world's tallest building, if you had a 10% increase in height from one to the next, that was a big deal. We're talking about increases in height of 60 to 70%, and we know there's more to come. So there are, these tall buildings are a fact of life. So what can we do to take advantage of it? Do you design to reflect the environment? If so, which one? You're living in Dubai at the base building, and at the top of the building, it's equivalent to being in Sacramento, California. The magnitude of difference on Burj Dubai alone, from the bottom to the top, is 14 degrees Fahrenheit, just in temperature. And that's just using the standard guides. They're actually monitoring the building now, and they're actually finding it even a little more than that. So taking advantage of height. This is really more a question for all the designers and engineers here at this conference.
The idea here is, if we truly reflect our environment, well, the cloud may make some sense. I mean, why do you travel long distance to get a cooler environment? Maybe you just build it taller, right? I mean, you save all the airplane. Remember, airplane traveling is very, very not carbon neutral, right? So there's no right answer to that. Just something to think about. But if you want a different environment, maybe you build it taller.
So other things to think about, or perhaps take advantage of, or perhaps be the subject of another paper. There are other differences, just physical facts of physics, if you will, between the ground and the top of a building, gravity. Building movement is something in these tall buildings. There's a lot of movement in the wind. Can you harness that in some way? Stack effect is a potential that we're starting to see harnessed on some advanced projects to try to induce a flow that is natural in the building, and differences like electrical potential between the top and the bottom of the building. So I think as Steve said at the beginning, we're in a new era. This is really a field that it's necessary, and I think given the combined presentation, it's necessary. We need more people up here. We need scientists, and we need physicists, and we need others to kind of think about this problem, because it is a new era.
One more point I want to make is we are not trying to, what we're trying to do is a little bit of, let's go back to the fundamentals. Think about the environment in a deeper sense, and we are not saying whether use or not use wind turbine, but we are saying if you truly want to just use 100% of the wind power, there are other ways you can do it than just use wind turbine. But wind turbine oftentimes is more than just as the previous speaker Roy mentioned, it's more than just a energy thing. It's a statement making. It creates different kinds of value than simply energy.
So thank you very much.
Thank you very much. Peter Weismantle from SOM, thank you. Again, very